Hi, my name is George, and with Andrew, I'm going to present you the meta-learning for recent segmentation on satellite image features project for CS330. One of the problems in computer vision is that image segmentation requires a lot of data. It is very expensive to have pixel-level labels and annotations for satellite images, and the satellite image data have high degree of diversity from region to region. Therefore, our objective for this project is to detect, segment circular features in satellite images with the fewer examples possible by using model-agnostic meta-learning techniques. For that, we use a dataset from the National Geospatial Association with circular features in that dataset with about 4,000 satellite images. To start the analysis, we use VGG16 for feature extraction, PCA for dimensionality reduction, in order to find out basically the cluster assignments used to implement the cluster split in the model-agnostic meta-learning experiment. In total, we found 8 clusters, which are indicated here on the table, and different regions with different number of images in different regions. One of the experiments we did was to identify a very quick and easy way with few shots to do object detection, multitask object detection. So the objective for this experiment was to use 5-shot detection for circular features. And the methodology we used was to get a pre-trained COCO checkpoint as baseline, fine-tune the RetinaNet architecture. We restored the box regression head, initialized the classification head from the COCO, and then we added a novel class. In that case, it is the circular structures. And because the RetinaNet is single-stage detection on the novel class, then the training and the inference was extremely fast. So we achieved a result of 78.12% accuracy, which is more or less on par with the state of the art on the object detection. With that, I will hand over to Andrew.
Thanks, George. Hi, everyone. I'm Andrew. In experiment 2, we did a few things. First, we constructed our baseline segmentation system using the UNet architecture, and then we ran a quick experiment to ensure that our implementation didn't have any issues and that our segmentation architecture can learn to segment on this task. We then adapted the baseline to work in a few-shot segmentation manner by using the MAML framework. With the MAML framework, we learn a set of meta parameters that then at test time with a few examples can quickly adapt to learn task-specific parameters to do well in that few-shot task. Here are the results of our experiments. On the graph to our left, we can see that our few-shot segmentation system can work well on our data set. We can see here in a K-SHOT2 setting that after 100 epochs or so, our system does learn in this few-shot manner and can achieve a mean intersection over union of 0.485. On the graph on the right, we ran an experiment to see what's the best way to construct our meta kind of data sets. We evaluated few-shot performance across different K settings by using like a random split scheme where examples are assigned at random to the meta training validation and testing set. We then compared that to the few-shot learning performance of applying a clustered split scheme where here the examples are assigned by the cluster IDs, which is derived from K-means, and then those cluster IDs are assigned at random to the meta training validation and testing. We can see that across all K settings, the clustered split scheme results in better few-shot learning performance. We then wanted to see how can MAML adapt to unseen geographic regions. For this experiment, we trained using only examples from the Brazil geographic region since there was a lot of diversity, and we can see that our few-shot learning can adapt to unseen kind of regions such as Saudi Arabia and also Venezuela, but it can adapt well to other geographic regions. We think that this is because other geographic kind of regions contain very different kind of image features, and probably more training or more kind of iterations is kind of needed for kind of MAML to learn to adapt better. So some main takeaways is that few-shot object detection can be achieved on this data set with some simple transfer learning, and we can apply that MAML framework to do few-shot segmentation, and it can even adapt to unseen geographic regions. We also include some future work to experiment with prototypical networks and to train both object detection and kind of segmentation in an end-to-end manner. Thank you.